Hello, this is my first video for you guys, and just to refresh your memory, before spring break we did local extrema and saddle points, so all of that has already been covered. Now we're worried about the absolute extrema along a boundary. So I would ask you to refer to that picture of the Denali National Park map. You have boundaries, and along those boundaries you have to check to see if you have high points and low points. And then also at any of the vertices of the boundaries you have to check for these high points and low points. Now if you can read this handwriting, it's because it's my wife's handwriting, and I'm trying to make sure that you can see this. So the process is no different than what we talked about before for doing local extrema. You're going to need to take the derivatives, first derivative with respect to x and the first derivative with respect to y, and you find any critical points that are located, and what you find is this point that's going to be 1, 3/2. Now, is it in the bounded region? So we have to check to see what the bounded region is, and the bounded region is given by this set of formula right here. And so if you graph that, that's the shape that you see right here of y equals x, y is equal to negative x, and y is equal to 2. And so this point 1, 3/2 is located approximately right about here. So it's in the acceptable regions. So we know we need to use that check for absolute extrema for that one. Now we also need to check the boundaries. So here's the next step, and let me see if I can move this up. Okay, so one boundary that we're going to check is y equal x, and when we check that, we substitute an x in place of any y that you see in the original equation. The original equation, if I can show you, is back up here. So we want to substitute an x in place of this y and an x in place of this y, and so you now see you have an equation that looks like this right here. After you substitute it in and you do your algebra and simplify it, you end up with this. You take your derivative with respect to x, since that's the variable that you have, and you end up with x is equal to 7/6. And then you have to figure out what the y is based upon the boundary. So you plug it into that equation, and so you get y is equal to 7/6. So is this point, which is basically 1 1/6, 1 1/6, going to be on the boundary? And again, let me get a different color. That point is going to be approximately right about here. So yes, it's going to be on that boundary. So this is something that we will definitely check and test. So we'll move it up and we'll check the next boundary. So we're going to check the y equals negative x boundary, and we're going to take and substitute a negative x in place of any y that you had in the equation. So there's the substitution. You end up with this expression right here. You take the derivative with respect to x, solve it, you get x is equal to 1/6, and then you get y is equal to a negative 1/6 because you're checking it for that boundary. Now, when you go back to your shape, that particular point is located right about here, and so that is not in the boundary, so you're going to disregard that particular point. So you have one more to check. So when we check y equals 2, you're putting a 2 in place of any of the y's. You end up with this function right here. Take the derivative with respect to x, and you end up with negative 4x plus 4. And when you solve that, you end up with x is equal to a positive 1. And when you plug that back in, well, there's nothing to plug in. The y is equal to 2, so you don't plug anything in. Is that point 1, 2 going to be on the boundary? And the answer is yes. It's going to be located, well, let's get a different color. It'll be located right about here. Oh, crap. Well, I really don't want to start over again, so it looks like I managed to delete my picture. So if I have to, I can always, no, I can't do that either. You need to just wind this, back it up, and get the original setup for that, and get it before you go on. So anyway, the equation you saw, we're going to move on to the next step here. And the next step, and I'll try to make sure I don't delete anything accidentally. What a beautiful first beginning, and the sad thing is I've already done this for like 7 other videos where I haven't screwed it up like that. Anyway, so we need to check the vertices as well. So you're not done just checking the boundaries, you have to check the vertices. And the vertices of that shape, which you don't see anymore, but the shape looks something like this. The vertices were the point 2, 2, negative 2, 2, and then you have the point that's at 0, 0. So these are all points that you need to check. So you have the critical point that you need to check. You have the boundary points that we had and found that work according to those things. And now we also need to check the vertices. And when you check them, it's just like in Calc 1. You're going to find the coordinate that you have associated with that, so you can figure out what this value is going to be. So for f of x comma y, for that function, you're going to plug in those points that you see over on the left-hand side over here and calculate what they will be once you plug it in to this. Well, just went ahead and did the calculation. You get 9.25, 9.08, 9, 5, negative 9, and 7. So when you look for the smallest value is a negative 9. That's your absolute minimum. And the largest value is this 37/4, 9 1/4, and that's your absolute maximum. So what you're going to do, again, as far as steps are concerned, you've got to find any local extrema using the techniques that you did from just the first derivative. You don't need to take the partial with respect to x or the partial with respect to y twice. And so you find the local extrema. Then you have to check the boundaries. So you check the boundaries for extrema. And you have to plug each equation in for your boundary. And then you also have to check your vertices. And after you've checked your vertices, you take those 3 things and you plug them into the function and figure out what is the biggest and what is the smallest. And that is your absolute max. And that's your absolute min. And so that's your process that you're going to follow as you go through this. So this is just like finding local extrema. This you have to do local extrema as well, but along the boundary. And then the vertices you find just by the graph or finding intersection points. So let's look at another one. And again, I'll try not to destroy this one. You have this multivariable function. You have this set of boundaries right here. If you graph those set of boundaries, you end up with this line right here. You also have x equals 4. There's another line. So that needs to be included as a boundary. And then you have y equals 2. And then you have the y equals a negative x. And if you identify those vertices, you have the vertice right there. That is the point 4, 2, 0, 2, 0, 0, and 4, negative 4. So those are going to be all values that we're going to check. So first step is to find the local extrema. So you do your first partials with respect to x and y, and you get the point 31. And is that point 31 inside the region? And the answer is yes, it's located right about here. So you're going to need to check that value. Alright, when we check the boundary y equals 2, then you plug a 2 in place of any y's that you have in this equation. You end up with this equation. Take the partial with respect to x, and you end up with 2x minus 6. Set it equal to 0, and you end up with that point. And the y coordinate is going to be the same as your boundary, the y equals 2. So the point 32 is located on our graph as well. We need to check the x equals 4. So wherever I have an x, I'm putting a 4 into the equation. We end up with this equation. Take your derivative, and we end up with y equals 1. after you set it equal to 0, that partial. And is the point 41 on your graph? And the answer is yes, the point 41 is located about right here. Alright, see if I can move it up and not destroy anything. We check the y equals x, negative x, and you plug that in to the function, and you end up with this equation. Take the derivative, you get x is equal to 1, and then the point 1, negative 1, is it on the boundary? And the answer is yes, so we need to check for this one. And then we do the 0, x equals 0, and we find out that when we plug that in, we get this equation. Take the derivative, and y is equal to 1, so the point 0,1 is also on our boundary. So we've got lots and lots of points to test here. We've got the point that's got 3, 1. We've got this point to test. We've got this point to test, which are on the boundaries of our shape. So we've got actually 4 points from there. And then we have all the vertices. We've got to test all the vertices. So again, let me see if I can move that up without messing anything up. Oh, good. Alright, so in this particular instance then, when you start testing, here's your critical point. You get a negative 6. Here are your boundary values that we got by doing that other process of taking and substituting. And we end up with these 4 values that you see right here. And then we have all the vertices to check, and we get those values. So when you look, the biggest one is going to be 20, so that's your absolute max, and the smallest one is going to be this negative 6, and that's your absolute min. So I'm going to do one more example where I write it out with my beautiful handwriting on this screen. Hopefully the pen will work right, and I'm going to pause this in just a second so that I can write a bunch of stuff down. Okay, remember to turn it back on. So this third example, you have a question where you're supposed to find the absolute extrema for this function right here, x squared plus xy, bounded by the region that is y equals x squared and y equals 9. And that graph is down here. You can do that first, or I did it second when I was actually working this out. But I look for local extrema first, and when I do that, I do my partial with respect to x, my partial with respect to y, set them equal to 0, and when I do that, then eventually I get x equals 0. So when I plug that back in place of the x, I get y is equal to 0, so I have the point at 0, 0, which is this point down here, the origin. Alright, then I checked, that's within our region, so we can include it. I checked the y equals 9, I plug the 9 in place of the y in that equation, take the derivative, and I end up with 2x plus 9. Set that equal to 0, and when I solve it, I get x equals a negative 4.5 for this. And that is not going to be in the boundary, it is way over here. So that point, negative 4.5, is not in the boundary. We're going to disregard it when we check. We need to check the other boundary. This is the second boundary right here, y equals x squared. I plug the x squared into the equation in place of the y. I end up with x squared plus x cubed. Take the derivative, which you see right here, set it equal to 0, factor in x, and I'm left with this part of the expression. And I went ahead and just did this part in my head without showing it. I have x equals 0 and x is equal to a negative 2/3. Now 0, 0, we've already done that point, so we don't really need to do it again, but this point also needs to be checked to see if it's okay, and negative 2/3 and 4/3 is okay, so that's a critical point that we need to check. So I've got those critical points, and I also have the vertices, and the vertices are 3, 9, negative 3, negative 9 right here, and then 0, 0 is also considered a vertice, even because that's the name of it for a parabola, is the vertex, so we'll count that as a vertice as well. If you're not sure how I got the 3, 9, I just plugged in the 9 in there, and so I had 9 is equal to x squared, x is equal to plus or minus the square root of 9, and that's where I got the plus or minus 3's that you see here and here. So now we're just left with substituting the numbers in and see what we get. So this was a critical point right here, doing local extrema, and we end up with y is equal to, or f of x comma y is equal to 0. This was a critical point along a boundary. Okay, and these are the vertices. There was another vertice, but we'll try it again. We've already done the vertice with the critical point back up here. So we'll just make sure everything is back to normal. Alright, so plug these numbers in. Here's the calculations. I showed every little step. I even showed fraction magic right here. That 4/9 is equivalent to 12/27. And so you can start comparing. These two numbers are between the 36, which is going to be your absolute maximum, and then the negative 18, that's going to be your absolute minimum. Now, in the past, this absolute extrema is a great extra credit question. I may still have it as an extra credit kind of question. I just don't know yet. I'm still working on my strategies for trying to figure out how to test. So anyway, we'll see what I come up with by the time we do our test next week. And I'm sure we'll have a conference, and I'll send an email of things to look out for part 2 of test 3. So, trying to make sure these are all less than 60 minutes. This one, no question, is less than 60 minutes. So, bye for now.